Hey guys, welcome back to Computational Biology with Python. We're going to continue on in our computer vision journey here with some feature matching. So this is kind of similar to the image matching that we did earlier, but it's a little more advanced. So I'm going to save this as feature match. So this would be good for a bunch of different things. So one thing that came to mind is, say you're an ecologist and you are setting up trail cams to find some sort of animal, and you have thousands of hours of video, and you know what the animal looks like, but you don't want to sit and watch 1,000 hours of video. If you had this go through the frames of those videos and was able to identify the features that you input and then find them in the video, you could say, oh, the animal appears at this many minutes, and not have to sit and watch it all, which would be very nice, right? But there's other, your imagination is, you can do as much as you can imagine with this stuff. So let's get our stuff imported. NumPy as np, import matplotlib.pyplot as plt, matplotlib inline, and we're going to define our display, how we display these images. So we're going to say image cmap equals gray, and then we're going to fig equals plot figure fig size equals 1210. And then we're going to say x equals fig add subplot 111, and then x imshow image cmap equals gray. Okay, and so why is that? Oh, I forgot. There we go. Let's try it now. There we go. Okay, so the example, I'm going to use the same example that the original author of this script used, and that is to identify a cereal box, because it's colorful and it's kind of fun, and it's just interesting, more interesting. So I found, I just Googled many cereals and went through pictures, so I found like a row of all these cereal boxes, and then I picked one that I could find similar, because the thing that was a little difficult with this is that cereal boxes change the boxes a lot. They don't stay the same. Cheerios is probably a safe one that they've probably stayed the same since I was a kid. But even like mini wheats, I was like, oh, that's the same. No, it's all quite slightly different. But I picked Apple Jacks, so that's pretty standard. That they've stayed the same, and so I picked. Which one did I pick? I picked like a flat on, like this image, right? Okay, so now what we need to do is we need to upload them. So I'm going to upload all cereal, I called it, and then I uploaded Apple Jacks. So, like I said, we could use. I don't have trail cam footage, unfortunately. You can apply this to other things, but sometimes it's fun just to have, do this with something other than biology data. So, all right, so let's start. I'm going to say Apple Jacks equals CV2.mread, and what did I call it? I think it was just Apple Jacks, right? Yep. So feel free, if you're doing this for my class, or if you're, do this with whatever. Like, it doesn't, when I'm grading and stuff, I'm not going to, GPG, I'm not going to care what, I'll be able to see that you've done the stuff. So if you want to try it with cars, like an auto show, or album covers, or something like that, go for it. Display Apple Jacks. Okay, so wait a minute, let's see. See, imread applejacks.jpg. Yep, here's my Applejacks box. It's kind of blurry. It's weird why it's giving me this and not printing. Did I mess something up here? Let's see. CMap equals gray. Fig equals plot fig size 1210. X equals fig add subplot. X dot m show image CMap equals gray. Oh. It's at a 0 here. Oh, no, that didn't. Let's do it. Okay, I don't know what I did exactly, but there was a typo in here somewhere. I just copied and pasted the source code and now it works. So look at your code here. If yours worked from the start, you saw a typo that I didn't. But anyways, all right, so here's Applejacks. Now we get rid of these arrays. There we go. There's all of our serials in black and white. Okay. Sometimes you just don't, like, I could have sat here for an hour and just not figured out what the heck's going on. Okay, so the first method we're going to try is brute force matching. And so we do this thing, we have an orb descriptor. So CV2 orb create. And so orb is a way of finding like key points and descriptors in your testing or the thing you're searching for. So KP1 DES1 equals orb detect and compute, and we're going to do it on, did I just call it Applejacks? Applejacks lowercase. Applejacks, and our mask is we're going to do none. And then KP2, oh, this should be KP1, not KP2. KP2 DES2 equals orb detect and compute serials mask equals none. Okay, so did I call serials? Yep, okay. So let's run this. This should not be all capital. There we go. Equals none. All right. So now let's run brute force matching where the actual matching is taking place. So we're going to say BF is brute force, CV2 BF matcher. So this is the command to actually do the matching now that we've identified these key points. Norm hamming is the method. Cross check equals true. Matches equals BF match. Nope. And now we're going to match those key points we identified above, right? So we're going to do DES1, DES2. So there's the objects. I'm in R mode with all these capitals here. Okay. Let's see. Did our matches there. Now we're going to sort our matches. So matches equals sorted matches. Key equals lambda x dot distance. So there's going to be like matches that are not as good. No comment there. So we just want the good matches, right? Because it's going to have a bunch of matches that are displayed. So let's do Applejacks matches equals CV2 dot draw matches Applejacks KP1 serials KP2 matches, and we want just the first 25 matches, so everything through 25. and then none, and then flags equals 2. And then we want to display Apple Jacks matches. How do I spell Apple right? Okay, so as you can see, where was Apple Jacks on here? We're all over the place here. So this isn't the greatest method. We got none. So this method, not the best, because we have problems where like this, the top of the box is different, right? And so it's matching a lot of the text, but it's not matching the greatest for just okay, I had to do a little finagling to get this one to work on Praxis. So what you need to do is you need to go to terminal. First thing we want to do is we want to do pip uninstall OpenCV Python. So you should have had that installed. It should be uninstalled now. And then you're going to do pip uninstall OpenCV contrib Python. Say yes to get rid of it all, and then you're going to do pip install OpenCV contrib Python. Alright, so we got rid of, the problem is we had too many, or I had two versions of OpenCV. I had the normal and contrib. Contrib has more packages. It's the base plus a bunch of like experimental other stuff. So now for this Sift technique that we're going to use, we run Sift CV2.Sift create. So that's the farthest I've gotten. So let's hope it still works. So KP1 des1 Sift dot detect and compute Apple Jacks none. And then KP2, so this is the same thing. We're going to get some features from each of these using this Sift method. And we wanted to do, I think it's just all serial, right? Oh no, serials. Was it serials? Yeah, serials. Okay. Serials. And then none. I'm missing detect and compute. Alright, now we're going to use brute force with the Sift method, so CV2 BF matcher, and then we're going to do matches equals bf.knn match. KNN means known nearest neighbor. It's actually used a lot in things like network biology, if you're doing like gene networks and things like that too. Okay. And then, so it finds the best matches for each descriptor from this set, is what that does. So now we're going to apply a ratio test, so good equals brackets. So less distance between the features is a better match, right? So if it has a good match, but they're all scattered, we know it's not a serial box, right? It's just random matches. But if they're all the matches, we cluster them together, then we have a better idea, because we want all those little lines from like this, we want them all to end up in the same spot, not like, you know, all over like it was before. So for match 1, match 2, in matches, if match 1 distance is less than 0.75 times match 2 dot distance. So if the match distance is less than 75% of the previous match, then it's a good distance. Good dot append match 1. Okay. So now we're saying y4, oh, it should be match 1, match 2. Okay. There we go. Okay. So now print length of total matches when matches. So we're going to print the length. Print length of good matches, so the ones that abide by our 75% rule, then good. Okay, total matches 4,900, good matches 57. So hopefully those 57 will send us towards the right box. Sift matches equals CV2.draw matches KNN, no nearest neighbors, Apple Jacks, KP1, serials, KP2, good, non, flags equals 2, display, sift, matches. Alright, I haven't seen this yet, so fingers crossed. Hey, look at, we're getting better. So this is our Apple Jacks box, right? And we have a lot of indication that that is an Apple Jacks box. And we still have some stuff kind of going around different areas, but pretty cool so far. I like it. And let's try one more called flan-based matching. So this is a fast library for approximate nearest neighbors. So it's faster than Sift, so if you're doing like a lot of different, like I said, like 1,000 hours of video, this is faster, but it doesn't find the best matches, but just general good matches. So Sift equals CV2.sift create KP1. Okay. So make sure I zoom out so you can see what I'm typing. So Sift CV2 Sift create, we did that. KP1 des1 equals Sift dot detect and compute Apple Jacks none. KP2 des2 equals Sift detect and compute serials none. Alright, so this is the same as we ran before. Typo in it. Okay, so now flan index KD tree equals 0. Index params equals dict algorithm equals flan index KD trees equals 5. Search params equals dict checks equals 50. Flan index KD tree. Flan index KD tree. Index. Inded. There we go. Beautiful. Alright. Okay, so now let's do flan equals CV2.flan based matcher. So now we're actually going to run the matcher after we found our parameters. So remember, we're making features, we're identifying features in both of our Apple Jacks box and also our serials, and then we're just trying to match them the best we can. K equals 2. Good. So again, we're going to bin our good results versus our not as good results. So match 1, oh, I did this before, match 1, match 2, and matches. If match 1 distance is less than 0.75 times match 2 distance, so we're just finding the ones that are, remember, close to each other because we don't want them if they're too far away. Doesn't matter if it's a perfect match but it's on a different serial box, that doesn't mean anything to us, right? So we just want clusters. Okay, let's run this. Oh, I love it when it runs the first time. Okay, so now we've done that. Let's see what we got. CV2 dot draw matches K and N, no nearest neighbors, Apple Jacks, KP1, serials, KP2, good, none, flags equals 0, display flan matches. Pretty good. So again, we've got quite a few. You can see the aspects are all going to this Applejacks box, but we're going to add one more thing. We're going to add a mask to it. This is the last thing that we'll do. So Sift equals CV2 Sift create, and then we're going to do KP1 des1 equals, actually, let's make life easier. I'm just going to copy this, paste it right down here because it's the same thing. There we go. So we'll run that. Now we're going to do our flan index KD tree equals 0. Index params equals algorithm equals flan underscore index KD tree trees equals 5. And then search param equals dict checks equals 50. Good. All right, flan equals CV2 dot flan based matcher index params search params. So remember, we just said we created our index parameters and our search parameters above, like we did the previous types of analyses. They're all very similar. We're just kind of changing some of our, either the algorithm we use, like Sift, or our indexing. Flan K and match des1 des2 K equals 2. Okay, so this is all done before, so now we're going to do some masking. So matches mask equals 0, 0 for I in range length of matches. Oh. All right. Okay. So 0, 0 means pure black will be added. So now we're going to reduce the distance between our features to get better matches. So match 1, match 2, in enumerate matches. So again, if match 1 distance is less than 0.75 times the match to distance, match mask I, is equal to 1, 0. Okay, so now we want to draw params equals dict match color equals 255, or no, 0, 255, 0, single point color equals 255, 0, 0. And then matches mask equals matches mask. Nope, sorry. Lowercase. Matches mask equals matches mask. And then flags equals 0. I hope this is. Of course, there's something to typo. Match mask. Matches mask, matches mask. Is it supposed to be matches? I assume so, because all the other ones are. There we go. Okay, so now flan. So what we're doing here? You'll see in a second. CV2 draw matches KNN Apple Jacks KP1 serials KP2 matches non draw params display flan matches. All right, so what we did is now we're showing all the features that we identified, unique features on both the Applejacks box and on the serial boxes. So you can see these are all the different features that we can see. And we've changed the line color to be a single color, so we don't have like a Technicolor thing, so we can really get an idea of what the best box that we're matching is. So this is pretty good. This actually worked out pretty well for using different pictures and things like that. But you can see it's not perfect. You know, you can still fine tune a little bit what you're actually your parameters. You'll never get it perfect. So you want to like a set of confidence interval. Be like, okay, if this percent match this small area, then that's the object detected, right? So, but this is pretty good. So that is it for feature detection. I hope you learned something. It looks like my video is a little chunky, so thanks for bearing with me, because it's a let's see if I think if I plug my computer in, it actually works better. So I'm running off that here. But regardless, thanks for bearing with me from my oh, look at that. Oh, I'm so smooth now. Sorry, that whole video is probably chunky like that. Thanks for bearing with me. I'm on tangents here. I hope you liked the video. I hope you can see the application. If you could do it with any sort of image, microscope images, or ecology, or if you're doing, if we used this on the sunflower heads, we probably would have gotten a lot better results than the really basic one that matching that we did earlier. But yeah, you get the point. So I hope you learned something. I hope you like this. I hope someone, if you actually end up using this, please like contact me on YouTube or whatever and let me know, because